let's take a look at the graph of this parabola, y equals x squared minus x minus 12. Now, one of the things I could ask you to do would be to find the x-intercepts. And the x-intercepts would be, well, let's see here. It'd be x minus 4 times x plus 3. The x-intercepts are going to be where y equals 0. So can anyone read off for me from this where the graph would cross the x-axis? Where is it going to equal 0? What values for x? 4 and negative 3. But if I had another parabola like this, say x squared minus 4x plus 4, that's going to factor a little differently. It's going to factor as x minus 2 times x minus 2. You could write it as x minus 2 what? Squared. Good. And really, my solutions are x equal 2 or x equal 2, right? It's just really one solution. And what we say about this is that x equal 2 has multiplicity 2. So we got a multiplicity of 2 for that root. And this multiplicity is something that I want to look at with you in this section. We're going to investigate the behavior of a function near its root, and the behavior is going to be somewhat determined by the root and its multiplicity. In fact, it's going to be very much determined by that. And for that, let's take a look at that link that I sent you on Desmos. So let's go here. And I've got three graphs. Y equals x squared, y equals x to the 4th, and y equals x to the 6th. Now, for the first one, you can see pretty clearly what the graph is, right? It's just going to come down and touch the x-axis at x equals 0. If you want to make your Desmos graphs a little bit more defined, if you click the tool in the upper right-hand corner, then click projector mode, they get a little easier to see. Kind of like that feature here. But let's take a look at y equals x squared. The 0 for that graph is at x equals 0. X equals 0 is a root with what multiplicity? 2. Right? Because it occurs twice. What about x to the 4th? X equals 0 is still a root. What's its multiplicity going to be this time? 4. And then likewise with y equals 6, we have a multiplicity of 6. But what's that going to do to the graph, or how is it going to be reflected in the shape of the graph? Well, let's kind of investigate that with the link that I sent you. And if you don't have the link, you can also find it on the welcome page when you sign into my Desmos account, or the class's Desmos account, I should say. So let's take a look at these using Desmos. Here's x to the 4th. Oh, okay. Is it much different? It is and it isn't, right? I mean, I guess the one thing that's similar is a couple things that are similar. It's symmetric. It kind of opens up, right, like somebody signaling touchdown. And then it touches the x-axis. It kind of kisses the x-axis and then bounces back the other way. How about x to the 6th? Do you expect something radically different for x to the 6th? Yeah, just more packed in together. That's a nice way to say it. So it kind of bounces off that x-axis, you know, so it comes one way, kisses the x-axis, and then bounces off and goes the other direction. Now, if I had a negative in front of these things, it's just going to do the same thing except open downward. Okay, that's fine. Let's shut these off. So that's behavior of those graphs. Let's take a look at what happens when you have an odd graph or an odd multiplicity. So y equals x to the 3rd, x to the 5th, x to the 7th. What are you seeing there? Does this have the same kind of bounce behavior that the other one did? Not exactly, because these go in opposite directions, right? To the right of the y-axis, this goes up and away. To the left of it, it goes down and away. So, okay, it's a little bit different behavior there. And so we're going to start categorizing these behaviors. Now, we're going to call these things, the first type of behavior we're going to call a bounce. That was these right here, where the graph just bounces off the x-axis and then goes back the other way. And this next one has a very deep mathematical term. The way it goes through the x-axis, it's called a wiggle. All right, I'm joking about the deep mathematical stuff. You can laugh and make me look good, all right? But the wiggle is just kind of our nice little shorthand for referring to this type of behavior. There's one actual last type of behavior, and that is when you have just y equals x, a multiplicity of 1, the graph's just going to go straight through. So let me summarize these for you in terms of their roots and multiplicities. So the multiplicity and then the behavior. So the multiplicity, if it's 1, then the graph's going to go straight through. It's going to go straight through the x-axis. It's not going to wiggle. It's not going to bounce. It's going to go straight through. If it's an odd degree greater than 1, so like 3, 5, 7, 9, then you're going to have a wiggle through. And finally, if you have an even exponent or even multiplicity greater than or equal to 2, what kind of behavior are you going to see? Yeah, the parabola, which has a bounce at that root. So those are your 3 different types of behaviors. Now, I'm going to add one little thing to this, and that is the so-called end behavior. And for the end behavior, let's look at our handout. There's a couple different types of end behaviors that you can encounter, and it's all going to depend on this term right here, the leading term. So you got some polynomial that has a leading term, and if this polynomial has an odd degree, so 3, 5, 7, 9, etc., then eventually your polynomial is going to have this kind of behavior. It's either going to go down and to the left, up and to the right, like this, or if this coefficient is negative, then leading coefficient is negative, then it's going to go up to the left and down to the right as you move farther out. Eventually, it has to settle down into one of these 2 behaviors. And that's just by knowing that leading term. That's all you have to know to see that that behavior is going to be true. On the flip side of things, if you had something of an even degree, all right, those can happen. So if your polynomial has an even degree, so it's going to be like a parabola would have an even degree, or a 4th power. Then the tails here, which is what I like to call them, the end behavior is either going to be both up or both down. It's going to be one of these 4. And I'm not going to ask you to remember these by name in terms of, the letters I'm going to give them. We'll call this A, B, C, and D, these different behaviors, just so we can kind of quickly refer to them as we go through this lecture. Okay, that's nice. Let's see if we can't make a prediction about something here. And for that, I want to look at problem number 46. So let me find that in problem 46. We're going to look at 2 different graphs. problem number 46. Let's see here. We're going to look at the graph of y equals p of x equals negative 1/8 x to the 1/3, negative 1/8 x to the 3rd, plus 1/4 x squared plus 12x. And we're going to look at q of x equals negative 1/8 x cubed. First things first, which of those four behaviors that we had here are we going to see when we look at this graph? So here's your two polynomials. Which of these four behaviors are we going to see? I've heard A, B, and D. We'll vote on it, right? It's an election year. We'll just vote on it, right? Math by democracy. Good there? Well, let's see if we can't be a little bit more scientific about this. The leading coefficient is negative, so that eliminates A and C. And the degree is odd, so that eliminates one more. It eliminates D, right? So it has to be, it's going to look like B overall. So it would look like B. Now, are these two graphs going to look a lot alike, or are they going to be somewhat different? Somewhat different if you're looking close to x equals 0, that is close to the x-axis. But here's what those graphs actually look like. And if you were to graph them on your graphing calculator, you can kind of mimic this with this window. Actually, you know what? No, not that window. But here's your two graphs. 1 and then 2. And you just really can't tell the difference between these two. It's just, in the end, they both behave kind of the same. So, and that's the point of looking at the leading coefficient, because the end behavior tells you a lot about this graph of the function. Now, if I zoomed in, say on the x-axis, I would see some differences. But in the long run, the only thing that really matters is this. This pretty much tells you the story of what's going to happen with the graph in the long term. Now, we're going to use this and some other things to see if we can't make some predictions about what some graphs are going to look like. So, before I move on from problem number 46 here, we okay with that conclusion there? Problem 46. I think if you wanted to view this on your graphing calculator, a good viewing window might be like negative 80 to 80, and then negative 4,000 to 4,000 on the y-axis. I think that would probably be a good viewing window. And you would see pretty much this. But like I said, we're going to focus on a few problems from the book, starting with problem number 10. Okay, problem number 10 gives us q of x is negative x squared times x squared minus 4. And they're also going to give us 4 graphs to pick amongst and decide what we think is what. So, okay. Well, let's do this. Can we factor this any further? Thank you. x plus 2, and x minus 2. So having it factored there helps us out, because we can look at this and decide where this actually equals 0. So let's look at the binomials. Yeah, binomials, and then the root, and the multiplicity, and finally the behavior. So my binomials here are going to be an x squared, an x plus 2, and an x minus 2. Okay. Corresponding to x squared, what kind of a root am I going to be looking for? What's the root of this term? Where does that actually equal 0? 0. Let's keep going. Negative 2 and 2. Thank you. The next thing I want to look at is the multiplicity. How many times is 0 a root? Twice. All right, so twice. Faith, what's that say for the behavior here? What kind of behavior are you going to get when you have a root of multiplicity 2? Good, that's the bounce. Nice. The multiplicity of this one. What's our multiplicity at negative 2? How many times does this occur as a root? 1. 1 for both of these. Now something interesting here, if I add up these roots and their multiplicities, they always add up to the degree of the polynomial. That's a nice correspondence. If you distributed this, you'd have a 4th degree polynomial, and we've accounted for all 4 roots. Andrew, what's the behavior of a root of multiplicity 1? Good, so straight through, thank you. And straight through again. Nice. So we've dissected a lot of this, but let's take a look at the end behavior and see if we can't say something about that. Our end behavior. Okay, end behavior. Well, you've got 4 choices there. Let's go back to that. Which of these 4 choices is going to be it? A, B, C, or D? All right, well, we can eliminate A and B, right? Because it's not an odd degree. And what decides between these two? Yeah, the negative. So you're exactly right. D. Thank you. So end behavior is going to be D. Wow, we know a lot about this graph, and we haven't even looked at its graph. We know a lot about what to expect. So here's your choices. See if you can't figure out which one belongs. Which one's the right one for problem number 10. Yes?
If the x and y's are reversed, would it be all different?
Yeah.
So you have to fix y.
Well, I mean, when you said x and y reversed, I was thinking of what you do when you find the inverse function. The graph would flip around the line y equals x in that case. What do you mean by x and y is reversed?
It had like a function that was like x equal y squared or something like that.
X equal y squared. Well, that is kind of reversing x and y. That would be a parabola that opens sideways. Yeah. So.
But could you still find your roots that way?
Yeah, you can still factor and find roots. Mm-hmm. All right. Addison, what do you think? Which which of these four looks like the right graph? Graph 4? Okay. Sam, is she right? She said 4. Think she's wrong? He doesn't want to correct you. He's being a gentleman. All right. Kennedy? Got to vote for 2. I mean, 2 seems to match a few things. But Eric's shaking his head like, no. Y'all wrong. Go ahead, Eric. What do you got? You got 1? Miles, do you agree with 1? All right. Let's think about what we expect. So, I mean, I think the end behavior tells us all we need to know. All right. The end behavior said that you're going to have an even function so that both of the tails point the same direction. Either they both point down or both point up. This would reflect an odd function, so would this, right? So both of these are off the table. Neither of those fits. Now, we wanted something that both pointed down, right? Because we chose end behavior, what was it, D. So we had end behavior D, so both of them point down. But does it match our expectations in other regards? Let's take a look at the behavior of this polynomial near the roots. At -2 and 2, what behavior did we expect from our polynomial? Straight through, right? So straight through and straight through. And then at 0, we wanted a bounce. Oh, okay, so that looks pretty good there, right? Yeah. Now, how come it can't be problem number 2? Yeah, the end behavior is wrong, right? The end behavior is pointing up in both directions, but we expected something that pointed down in both directions. It's kind of like a parabola that opens down. You okay with that? All right. All right, thank you. Anything else on problem number 10 here? Eric? That's a great question. In fact, we're going to practice that a lot with the rest of our handout. Okay, so let's go back to our handout. And in all honesty, I think I'd redo this a little bit. You don't need 2 different spellings of straight through. I think it's enough to have 1. All right, but whatever. Put straight through 2 different ways. Let's start by looking at problem number 20 and see what we expect from problem number 20. Now, with problem number 20, let's see if we can't get that focused a little bit better. There we go. Problem number 20, you've got your polynomial, which is a product of these 3. So our binomials would look like this: x minus 3, x plus 2, and 3x minus 2, like that. Now, it's not really written, but what's understood to be the exponents for these polynomials? Yeah, I should probably call them binomials. It's understood to be a 1. So the multiplicity here is going to be 1 for all of them. So, Eric, this is getting towards your question, but hang on through problem 26, and we should see a little bit more about the answer to that. What's the roots of these polynomials? Good. -2 and +2. Now, if your root has a multiplicity of 1, what's going to be the behavior near that root? Straight through, straight through, straight through. Straight through. Straight through. Straight through. Yay. Let's see that indeed our polynomial matches what we expected. Oh, you know what? There's one other thing that I want to look at here first. If we add these up, we get 3, and that's the degree of our polynomial. So with a degree 3 polynomial, and if I multiply these out, would I have a positive or negative coefficient? What would my x cubed term look like? Positive or negative coefficient? It'd be positive, right? So the degree 3 coefficient, positive coefficient, which one of these polynomials or which one of these behaviors do I expect? A, B, C, or D? Yeah, we can eliminate these real quickly, right? All right, because it's not an even degree, and it has a positive coefficient, so it should look something like this. Let's see that happens. And if you flip over your graph onto the back side, looks pretty good. You know what? I cheated here. I was wrong, too. I put x equals 2. Yeah. What should the root be? 2/3. Thank you. Okay. So let's see. So we have roots at 3, -2, and 2/3. So here's our root at 2/3. Here's our root at 3. Here's our root at -2. Yeah, okay. 2/3 and 3. So does it match all our expectations? Yeah, I'd say so. We have the proper end behavior, which is here. We have the proper roots, and the behavior at the roots, right? We had straight through, and straight through. Yay. Looks like we nailed it. All right, how are we looking on problem number 20 there? All right. Let's try another one like this, and I think, let me just double check if I have this one here or not. Yeah, let's take a look at problem number 26. All right, so with problem number 26, let's come down and take a look at our chart, or make a chart, I should say. Not that one, this one. There we go. And Eric, I'm hoping this one is what you're looking for. Now, our binomial terms are going to be x plus 1, x minus 1, and x minus 2. No argument there. What about the roots of these polynomials? Dwayne, what would the roots be, please? Perfect. Thank you. Grant, what would be the multiplicities involved? Cool. Eric, are you seeing where those are coming from, the multiplicities? Exactly. It's just the exponent. How often does it occur as a root? That's your multiplicity. What degree polynomial is this if I multiplied it all out? Good. So 6 would be your degree. 6th degree. Now if it's a 6th degree polynomial, let's take care of that right now. It's a 6th degree polynomial. What type of behavior is it going to have in terms of its end behavior? So it's going to be D for the end behavior, right? It's going to be this one. They're both going to go down like this. That's at least what we expect. So, okay. So end behavior would be D. Would be a D for the end behavior. It wouldn't go down if it was positive, but is it positive? Yeah, you got that negative there that's kind of sticking out in front. That's what makes it open down as opposed to open up. So what you expect is kind of what we see here, which is this much right here. That and that. There's your end behavior. Now, let's see what else we expect. And this is where we can use our little Desmos demo here. So the first thing I'll do, and if you haven't already done it, you can shut off these other graphs just by clicking on them. But the first thing I'll do is click these, and you can see the end behavior. But what about our root at -1? This graph's going to come up and touch the x-axis, but what's it going to do there? Let's take a look here. Let's take a look back at our little table and find out. At -1, we had a multiplicity of 2, so what kind of behavior does that mean? Bounce. So that means this should go up, touch the x-axis at -1, and then bounce. Let's see if that's true. So we'll go back here, and here's the point where you can ooh and ah. You ready? 1, 2, 3. Ooh, ah. All right, cool, because what had happened? It came up here, and it bounced. Wow. Just like we had predicted, right? Nice. Let's go over and look at the next part of this. So the next part of this, let's see. That's the one I want. So the next part of this was over here, right? And again, we need to figure out a behavior. This time we had a multiplicity of 3. So Sam, what happens with something with a multiplicity of 3? Good. Does the wiggle? So let's test it out here. Let me see a wiggle. Ooh, ah. Cool. It does exactly what we expected, right? It kind of wiggles through there. All right. Notice the difference between the bounce and the wiggle. Finally, let's get down to the last one. The last one was our term at x minus 2. And x minus 2 had a multiplicity of 1. So what's going to happen with a multiplicity of 1? Yeah, it's just going to go straight through. I don't know why. Maybe because I'm putting this on YouTube. I don't want to abbreviate through, T-H-R-U. Or just, I don't know. Anyways, let's see here. And for the coup de grace, let's put in that last little bit there. Is it this one? No, this one right here. There we go. Ooh, ah, pretty cool. So it matches exactly what we were predicting. And you can take that and copy that onto your own handout there, because on the back side, and more ooh, ah. All right. This one's going to come up to 2, bounce, come down to this minimum, cross through the y-axis right there at -2-ish, and then it's going to kind of wiggle through at 1. So up here, wiggle through, and then what happens at x equal 2? At x equal 2, we had a straight through. So it's just going to plummet straight through, like that. All right, so there's your polynomial. There's so much you can tell just by looking at the form of this. We can really do a pretty good job of graphing this without graphing too many points, just by knowing the overall behaviors of the roots and the end behaviors. Okay. How are we looking on that one? Is that all right? Is it pulling everything together? You've got roots, multiplicity, and behavior. Those are the things that you should be synthesizing together. Nice. Any comment on this before I move on to a couple more here? Let me skip down to the last one here on our handout, problem number 42. And might help if we looked at that together. So we're going to have to do a little bit of factoring here. And a lot of times you are going to have to do some factoring. In fact, in the previous one up above, you'd have to do some factoring. You'd factor out an x cubed, leaving behind x squared minus 9. X squared minus 9 can factor further though, right? So how does x squared minus 9 factor? Thank you. X plus 3x minus 3. So if your polynomial isn't given to you factored, you're going to have to factor that yourself. All right. Now, what I'm going to do here, hopefully, is kind of a familiar trick, and that is factor by grouping. Wow. I'm glad you're tuned into the lecture. All right. So, what can I factor out of the first pair? Yeah, you factor out the x cubed and it leaves behind x minus 2. So I'll put in x minus 2 here, and likewise here. Okay, well, because this term is shared by both of these, I can further factor that like this. Now, the one factorization that is easy to forget because you don't use it very much is the factorization of the sum of cubes. This term factors into those two terms. So it factors into the binomial. You cube the x and you cube the 2 to get that binomial term. For the trinomial, you take the first term times itself, that's there. Second term times itself is here. And then this times this is the middle term. The one thing I've forgotten to remind you about is the signs. And those of you who've had me last semester might remember this little acronym. What's that help you remember? Good. Same sign, opposite sign, always positive. What's the importance of this factorization? Well, you can see the binomials now, right? X plus 2 and x minus 2. So you have to have those things factored. See if you can't finish this up. Find the roots, the multiplicity, and the behavior. This one is not going to factor into any real numbers. You're going to get some complex numbers, and those aren't going to be things you're going to find on the x-axis, so I'm just going to leave that one there. Yeah, maybe I can do this. X squared minus 2x plus 4. That has complex solutions. You can see that if you investigate it with the quadratic formula. Yes. It will. You will see. I mean, it does affect the graph. It's kind of tough to say in which way. What you won't see is where it crosses the x-axis, because it doesn't contribute to it that way. Much like, you might be able to kind of envision this graph. Y equals x squared plus 4, right? It's going to be your parabola moved up 4 units. So it's just going to look like this, but it doesn't cross the x-axis. That doesn't prevent you from looking for it. If you look for it and say, all right, well, where is that equal to 0? What you get is plus or minus the square root of negative 4, which is plus or minus 2i. It crosses the x-axis only in your imagination. So you're going to see that with this. If you try to solve, you get complex roots. So it's not really going to contribute here, but it does change the behavior. just not in ways that we can easily predict and relate to. Okay. Selena, what are the roots here, please? All right, so negative 2 and 2. And the multiplicities, 1 and 1. And then the behavior would be straight through. So straight through for both of them. Nice. Awesome. Thank you. Let's take a quick look at this one on our graphing calculators. All right. Some people need to borrow one. Come on up. I forgot to do it at the beginning of class. You're welcome. Yeah, I'm getting really familiar with your means of exchange here. Yep. What do we expect from its behavior in terms of the end behavior? End behavior. Well, it has an even degree, so we can eliminate those two. Is it going to open up or open down for its end behavior? Up. So end behavior would be C, and somebody said C, thank you. So let's do a quick graph of this. Let me clear out all the stuff here. Go to the y equals key. Now you can type in either one of these that you find convenient, either this one or this one. I'm going to type in that first one. So it's going to be x raised to the fourth minus 2x cubed. Now when you enter in the exponent, you got to hit the right arrow to get out of the exponent. Plus 8x, let's see. Yeah, plus 8x minus 16. Bam. Now I got to set a window. And I know the roots for my polynomial should be between, say, well, negative 2 and 2. Those are the only two roots. So let me get a window that's a little bit bigger than that. Let's go negative 3 to 3 on the x-axis. So when you hit the window key, type in negative 3 to 3. And now it comes down to the y-coordinates. Like, what do I want to do for the y-coordinates? I don't know. Yeah, so kind of a nice, easy fix. Once you've set your x-coordinates, you can also make your calculator do the rest of the work by hitting zoom and then 0. You don't even have to scroll up to see it. You can just type in zoom, then press the 0 key. That'll adjust your y-axis so that it fits the x-axis. And I get a graph that looks kind of like that. Okay, not bad. It shows us roughly what we expected. We expected a behavior like this, straight through here, but there's this minimum point over here. Might want to look at that. Let me take care of one thing here. Notice how my y-axis looks like a mess. Can anyone figure out why? Y scale. If you go back, choose Y scale. Right now I've got Y scale set to 1. Let me choose something a little bit bigger, like maybe 20. All right. And then when I go back and look at things, I get a much cleaner looking graph. And you can better estimate points for that. So there's our graph. And if I was to be a little bit critical of myself, maybe I go out to x equal 4 or 5 just to see a little bit more of the right tail. And there you go. But it opens up just like we expected. Okay? So it does have the proper end behavior. How are we looking on these graphs so far? Corresponds between roots, graphs, and multiplicity. Behavior at those roots. All right. Let's take a look at another one on our graphing calculator. That's going to be problem 62. Y equals x to the fifth minus 5x squared minus 6. And the first thing to do is to graph it. And I'm going to suggest that we graph this between -4 and 4. Before I graph it, let's make some predictions about the end behavior. End behavior. Which of those end behaviors do you expect? A, B, C, or D? Well, let's see. How come I can eliminate C and D from the end behavior possibilities for this one? So the degree was 5. Yeah, the degree is odd, right? So we can eliminate these two. It's not C or D. So what is it? Well, it's either A or B. Yeah, the leading coefficient, even though it's not really written, it's understood to be 1, which is positive. So the end behavior has to be A. Nice. Let's put that graph into our graphing calculator and then remind ourselves something else about this function. So let's see, window y equals, so we got x raised to the fifth. Press the right arrow to exit the exponent. Of course, that raise key is right above the division sign. Minus 5x squared minus 6. And the hint that I gave you was to set it up on the x-axis between -4 and 4. So I'll do that, -4 to 4. What am I going to do about the y-axis? Where should I set things up on the y-axis? Zoom 0. Once you get those x-coordinates set, hey, let your calculator do the dirty work. Let's do zoom 0. Let it figure things out. Earn your money. And wow, looks like I adjust the scale there again. Right? Because my scale, whatever this is, -4 to 4, this way is huge. So let's see. You probably get away with y scale equals 200. I'm not seeing a whole lot of detail around the x-axis, right? In fact, it looks kind of flat, doesn't it? Now, there's two different ways that you can investigate, what's happening here. You can just change the y values so that we don't see all this extra stuff. I mean, you kind of know what the end behavior is. We predicted that before we even graphed it. So one way you could do things is just to adjust the y-axis and maybe not go down as much. Maybe go down to, let me be conservative here. Let's go -400 to 400. We're still going to do some more work here. And at least I see a little bit more detail. But I'm still not getting exactly what I want to see. I want to see what's going on really close to the x-axis. I want to see where it crosses the x-axis. So let's do this. Hit the zoom key, and then the first selection is zoom box. I think we've used this before, right? So zoom box. And now take your cursor with these arrows, and let's go someplace over here around -2.5 or so, and then just go down a little bit. This is going to be one corner of your new viewing window. When you get to a spot that you're comfortable with and doesn't have to be exactly mine, press the Enter key, and let's drag up. So we're just a little bit above the x-axis, and then drag to the right. And when I think I've got what looks like a good viewing window, then I can press the Enter key one more time. So let's press that Enter key one last time once you've got the corners of the box set. And now, okay, that's looking a lot better. I can see much more detail in that graph. Are we good with those little tricks here? All right. Because one of the things we'll do is we'll try and find a minimum point here on this graph. That's actually one of the questions that they ask here, is to find that minimum point. Before I get there, let's look at part C here. Part C asks for the domain and range. Let's think about the domain and range. The domain corresponded to which coordinate? Nice, the x-coordinate. So what could the x-coordinates be? Center of restriction, Faith? All right, all real numbers? Yeah. There's no problem putting in any number, right? There's no zero denominators. There's no negatives underneath the square root. There's no negative logs. Nothing. No problems at all. So the domain would be -infinity to infinity. How about the range? The range is the y values. Where's this graph going to start and end up? I think it's going to go a little bit lower than -5. -infinity to infinity. Does anyone remember the fancy way that I gave you to write that? Script R. Yeah, script R. That could be a bonus point when used correctly. I always got to say used correctly, because then I get somebody who puts like a script R next to every problem and then wants 20 bonus points. No. When you use it correctly, then it works. All right. There's one last thing here, and let's see if we can't find the minimum point here. Now, if you're not quite keeping up with this graph, we're going to do one more like this to find a maximum point, but try and keep up with this as we practice here finding a minimum point. If you look at this graph, it kind of has a little dip here, doesn't it? Graph goes down, and that point's called a local minimum. It's lower than anything nearby. So to find that, you hit the second key and then the trace key that takes you to the calculate menu, which is what I've got here, second trace. Is there an option here that looks promising? Yeah, the third one down. You can just type the number 3. And your calculator is going to ask you to focus its attention. Say, okay, where do you want me to look for this thing? That's what it's looking for. So you can scroll with your arrow keys and get someplace kind of close. Doesn't have to be very close. And then press the Enter key once. That sets your left bound. You see a little triangle and a line here saying, okay, I'm going to look to the right of this line because this is my left bound. Now I don't feel like actually, holding down the right arrow key forever. So I'm just going to cheat. I'm just going to type in the number 2, which is another way that you can come up with your bounds. When I do that, it puts this line on the bottom. Press Enter. And now you've told the calculator where to look. And for reasons that I won't explain, it's asking for an initial guess. Just press the Enter key one more time. And you should get about 1.2599. Is that what you guys are getting? How many got that? All right. Now, if you didn't keep up, I understand that. I went kind of fast. I'll give you another chance to work on that. But the minimum point, the local min, is at x equal 1.2599, and y is negative 10.7 something. So local min is at 1.2599 and negative 10.762. Yay. All right, so we got a lot of that. Yeah, Sarah? Rounded to? Yes, yeah, absolutely. In fact, I was thinking about that myself. I'm like, okay, I should at least be consistent with myself. Because I was initially going to round it to negative 10.76. I'm like, well, that'd be a little confusing because one I'd round to 2 and the other one I'd round to 4. So, yeah. No, I will tell you where I'm really concerned about. I'll tell you where I want to round to. Yeah, thank you. Okay. Let's do one from section 3.1 to kind of round things out there, because in 3.1 we didn't touch on one thing that's true about parabolas too much, and that is, depending if your parabola opens up or down, you're either going to have a minimum value or a maximum value. So let's take a look, like I said, at problem number 54. Which is this one. So a soft drink vendor at a popular beach analyzes his sales records and finds that if he sells X cans of soda pop in one day, his profit in dollars is given by this much. So, okay. Let's see if we can't figure out a few basic things about this graph in order to at least start graphing this. Let me put that function up here for us. This is problem number 54. Here we go. P of x was negative 0.001 x squared plus 3x minus 1800. Ugh. Ugly looking little polynomial there, but that's okay. Let's take a look at this polynomial, though, and think about the end behavior. So we're tying it in a little bit with section 3.2, even though it's a problem from 3.1. What's the end behavior going to look like? You had those 4 different options. I had one vote. Here's some other voices. Yeah, should be D, right? It has even degrees, so it's either C or D, but you have a negative leading coefficient, so it's going to open down. Okay. Well, that's good, because if it opened down, then I'm going to have a maximum at some point to this graph. So the end behavior is going to be D. Our graph is going to look something like this. All right. And at that point, we're going to have a maximum. So X and Y, that's what we want to find. Because they really ask us for 2 things. They ask for the number of cans sold, that's your X value, and then the maximum profit. That's your Y value. So I want both of those. Well, let's see if we can't get our calculator to give us some answers here. Miles? Correct. Even though there's a 1 here, the degree is just determined by that term, the leading term. So yeah, so you don't have to combine them and say, 3 or 4 or 5 or whatever the case may be. It's just that leading term. Oh, wake up. There we go. Good? All right, thank you. So let's think about this in terms of a graph. We need to figure out at least where to set it up in terms of the y direction, right? Or the x direction. Now, hopefully this guy is going to sell enough cans to make some money. I'm going to ignore this term. What does he start out the day at? Yeah, negative 1,800. He spends $1,800 for all his cans of pop. He's $1,800 in the hole if he sells 0 cans. So that's your y-intercept. Let's see. Well, if x is the number of cans, 1,800 divided by 3 is what? 600. So we should at least go to 600, maybe more than that, maybe 1,000, so that we can hopefully start to capture some of that curve coming back down. So let's see. So let me graph. Let's set up our window between 0 and 1,000. I still have to put in my equation yet. If I'm going 0 to 1,000 on the x-axis, what would be a good idea for x scale? How often do you want to see your tick mark? You don't want to see 1,000 of them. So what would be a good place? 50? 100? Let's go 100. Y minimum, I'm going to set to 0. I mean, you could set it lower if you want. You could at this point do zoom 0. But let's just give it a shot here. Let's see. Let's go up to 200. 200. Let's see what we capture. I'm not really sure what we're going to see, if we're going to see anything. No. Oh, I forgot to put the function in. It might help out. Negative 0.001 x squared plus 3x minus 1,800. We could also be a little bit more scientific about this and let our calculator do the work when you hit zoom 0. Let me see how my guess is. Still thinking. You see that little circle there. And boy, we didn't catch much of this graph at all, did we? I mean, I knew that it was going to be below the x-axis, but boy, he's got to sell a lot of cans before he even breaks even. So, all right. Let's adjust things out the y-axis a little bit, or out the x-axis. I need to sell a lot more cans. So let's go up to 3,000. I'm going to let x scale equal, say, 500. And we'll jump up to 500 for y max as well. And with these settings, hit the graph key. Let me give you a second to catch up to those settings. No matter where you're at, make these your window settings. So on the x-axis from 0 to 3,000. On the y-axis from 0 to 500. Because after we get this graph, we're going to want to find the maximum. All right. Bam. There we go. So because this parabola faces down, it has a maximum. Now, with our settings, I think you can actually pretty much read it off. But if you hit the second key, then the trace key, you can find the maximum. Left bound for the maximum, let's go 1,000. Right bound, we'll maybe go 2,000. And then to find the maximum, just press enter. It should quickly zoom in. Now, this is kind of interesting. Do you think that the maximum is at 1,499.9999 cans? What's going on there? Yeah, it just didn't round good enough. Yeah. So it should be the number of cans sold is 1,500 and the maximum profit is $450. But be careful what's being asked for. Do you want the x coordinate or the y coordinate of the vertex as the answer to your problem? All right. How many people were able to get their way to the maximum this time? More of you? All right. All right. That's good. Any comments or thoughts on problem 54 here? All right. Let me give you some homework. For homework, try 9 through 25, 31 through 41, 45, 47, 51 through 57, 63 through 69, and 73. That's section 3.2. It may sound like a lot, but I'll give you 2 days to do it, okay? Nice. Good luck with that.